Good day. I am Peter Rony, Professor Emeritus of Chemical Engineering at Virginia Tech in Blacksburg, Virginia. This YouTube video is about enrichment chemistry, and before I go further, well, a lot of what I've said may seem rather esoteric and theoretical, so let me now illustrate at least one important principle of enrichment chemistry by a practical example. We start with a molecule, a dangerous molecule called DDT, which is short for dichloryl diphenyl trichloroethane. Here are two chloride atoms, and here are the two phenols. So this is chlorophenyl, you have two of them, so I have dichlorodiphenyl. And then here the red entity is an ethane structure, and you have three chloride atoms, and so the structure is called trichloroethane. And I got this image from this website. And if you see this URL at the bottom of subsequent figures, what it means is that I'm giving credit to the location where I obtained an image. I really like Google images, and I use it all the time to search for keywords. And this example, the keywords that I've been using are bioaccumulation and biomagnification and also amplification. And if you were taking an environmental science course or group of courses, you would encounter these keywords regularly. Before I go further, here is an excellent PowerPoint presentation that I encountered on the internet. I don't have the URL, but if you use Google search for biological magnification, you should locate it. It's a PDF presentation, and I'm very impressed with it. Well, I now would like to focus on the role of DDT in an ecosystem. This is an environmental science topic. Well, I take you to Borneo, an island in Indonesia in Southeast Asia, and I don't know how many decades ago, but here was the issue. There are lots of mosquitoes. And why? Because there's a lot of rain in Borneo, and the atmosphere is humid, and there's rapid vegetation growth, and lots of mosquitoes, which cause malaria. So the friendly folks in Borneo said, well, let's get rid of the mosquitoes, and let's spray DDT all over. Unfortunately, there was an unintended consequence. In fact, there were two of them. So let me look at the top one. DDT is an indiscriminate insecticide, which means that it will not only kill mosquitoes, it will kill many other types of insects. In Borneo, the case of it killed parasitic wasps, which were plentiful and kept control over insects. So this is a natural predator for what? A caterpillar. And this caterpillar is called a thatch-eating caterpillars. So because the parasitic wasps were killed everywhere, the caterpillars just kept multiplying, and there was an abundance of caterpillars. And what happened? Well, they ate the roofs off the villagers' houses. This is sort of a funny example, but it's quite tragic. So this is the top path, and there is a bottom path which I will not discuss, and you can learn more about this ecosystem situation by going to this URL at the bottom. Now, a more common example of DDT in ecosystem is the following, and this goes from dissolved DDT to zooplankton to small fish, large fish, fish-eating birds. And I'll show you another image, but this is an example of bioaccumulation. DDT in water is very insoluble. However, zooplankton, such as in the ocean close to shores, concentrates enormously the DDT. So if you have a pound of zooplankton and you measure how much DDT is present, you'll learn that the amount of DDT to the amount of zooplankton is in the neighborhood of 0.04 parts per million. Well, small fish eat the zooplankton, and the DDT that is contained in the zooplankton is transported within the fish to fatty portions of their cells. Well, large fish eat the small fish, and large fish probably have more fatty regions than small fish. And then what happens to the large fish? Well, they're caught by eagles, cormorants, other birds, and when you analyze the concentration of DDT in the birds, it's really very high, and the fatty regions is 25 parts per million. So if you go from dissolved DDT to the DDT in the fatty tissues of birds, the amplification is 10 million, which is huge. Okay, let me continue. Here is another image that makes the same point, and we start with dissolved DDT, but then another location is sediment, so the DDT adsorbs on the sediment at the bottom of, say, a lake. And then there's vegetation, and there are different types of fish. There's also algae, and finally at the top of this chain there's a cormorant. The cormorant eats the fish eats the algae and zooplankton. The zooplankton they don't eat, but they just attract the dissolved DDT, and here's another example, another image of food amplification. Now this image is from article that I encountered using Google Images, and here at the top is the title and where this article is published. And this really makes the same point. So at the very bottom of this image you have what they call primitive producers. Primitive plants and animals that are the first step in concentrating DDT dissolved in water. And then there's above them there's what they call the primary consumers, which are these types of animals that consume the primary producers. And then there are the secondary consumers, which are small fish, eel, minnow, and all that, they eat the blowfish, clams, mud snails, and all the bay shrimp. And then, so these are really the large fish, and below them are the small fish. And now we have a variety of birds that consume these large fish. And as you look at the common tern, the cormorant, the ring-billed gull are fish at the shorelines on oceans, and osprey is a land raptor. Green heron, I think they exist in southern Florida. So here you have the birds that concentrate DDT and are subject to death because of it. Now here's a new term that I encountered using Google Images. This is called a bioaccumulation pyramid. It's sort of is analogous to the food pyramid that you've seen on food packages. So what this pyramid says is, well, there are tiers. Tier 1 are the zooplankton. They call it planktonic feeders, algae, photosynthetic organisms, corals. That's tier 1. And tier 2 are what they call grazers. These are small fish and small animals, although turtles are certainly potentially large. And then tier 3 are large fish, humans, barracuda, predatory fish. So squids, octopus, and even humans. So this is the pyramid from the very elementary organisms through intermediate animals and finally to the highest level animals. Here's an image from Google Images that shows the amount of DDT and another pollutant, polychlorinated biphenyl, PCB, on different seabirds. And as you can see, some seabirds are vulnerable to having a lot of DDT. Look at the bottom, the glaucous gull, whatever it is. And so here's a whole series of seabirds, and here is how much DDT and PCB is in them. I like this image. This is my favorite image for demonstrating biomagnification. And in a sense, this is similar to an image or two I've shown. Let us start with a value of 1 for the concentration of DDT in water. Well, producers, zooplankton, algae, producers, I'm not quite sure what they are, they concentrate the DDT by a factor of 1,000. And the zooplankton consume the producers, whatever they are, and they further concentrate the DDT, so you have a ratio in parts per million of 10,000 here to 1 in the water. Small fish eat the zooplankton, large fish eat the small fish, and fish-eating birds eat the large fish, both in lakes and in oceans near shorelines. So when you go from water to fish-eating birds, the magnification in the DDT concentration is a huge 10 million, which is awesome. By the way, note that DDT is not reacting at any of these levels. It is highly unreactive. It stays in ecosystems for a long time, and all it does, at least here, is move from one location to another. And in this image, you can observe that there are 1, 2, 3, 4, 5, 6 different locations. And this is an example of what I mean, that for a single selected molecule like DDT, in nature it can be present in multiple locations. And that, in my opinion, is chemical engineering, which is part of enrichment chemistry. So let us apply my enrichment chemistry concepts to this DDT ecosystem. First question, what is the identity? And that's simple, the molecule DDT. Next question, what are the locations? Well, you've seen them. Water, zooplankton, small fish, large fish, fish-eating birds. And what is the DDT doing? Well, it is moving from one location to another, and it certainly does not undergo reactions. It's inert. And then a much more difficult question, which requires analytical chemistry measurement, is the amounts in these different locations. And as you've seen on the preceding image, the amounts vary enormously from 0 point something parts per million in water to 25 parts per million in birds. Well, we got a lot of DDT everywhere throughout the world, certainly in the United States, South America, Southeast Asia, and Africa. How did it get there? Well, it was manufactured in large quantities starting in the 1940s. And let me show you how it became present in ecosystems. Now, I enjoy this series of slides because some of them are really amazing. So here's one obvious method, spraying of agricultural fields. Here's another one. Here we have a fogger, a truck that goes up and down the streets of residential neighborhoods and provides a fog that settles on lawns and tree leaves and is supposed to serve as an insecticide. Here in the lower left corner you see workers with nozzles that are spraying DDT in a field. But they're better images. So here at the top left is a fogger, and here you have two people, I think they're two women, who are enjoying the fog spray. Hey, it's cool. And after having the spray, I will have no insects on me. And even more remarkable and hilarious is this image in the lower right-hand corner. Here we have a public swimming pool, and here we have a DDT fog generator, and it is spraying the swimmers. And why did they do that? Simple. They thought that polio was caused by insect bites. So how do you solve that problem? Well, you apply DDT and kill the insects. And here you have all the swimmers saying, hey, this is cool. I will be bite-free and I will not get polio. Well, inside the home, you'll find DDT, and here's a product called Black Flag Aerosol Insect Sprayer. Pretty dangerous product because you spray within a house and you are very likely to inhale the sprayed droplets, which are dangerous. So how dangerous is DDT? Well, here's a summary that I got from Google Images. Here at the upper right is the structure of DDT, and here are all the issues. An organochlorine insecticide, very nonpolar, which means it doesn't dissolve in water. It was banned in most developed countries in the 1970s and 80s. that was decades after it was first used in the 1940s. So it took us decades to figure out that it was dangerous and why. And in humans, it's now known to cause birth defects, damage to nervous systems, and cancers. And in the poorer countries, it's still used, which is a worldwide problem. And here is a can of DDT powder. You spread the powder over blankets and on floors and walls inside residences. Here's a quote I found using Google Images, and I think it's an excellent quote, popular by E.B. White, a famous scientist. And I like the sense, our approach to nature is to beat it into submission, which is what we've been doing until now, the 21st century, when we are more thoughtful about what we are doing. Can't say we are successful at eliminating, beating into submission of nature, but it's a lot better now. Here's an example, the icon of the United States, the American bald eagle. It's a beautiful, large bird. The problem is that the bald eagle eggs, because of the accumulation of DDT in eagle fatty tissues, the eggs are, the shells are very thin, the embryos are mutated and dead. Here's another example of a nest. You have hatched eggs, and look at the dead hatchlings. Well, it took until 1960, after 15 to 20 years of DDT spraying, for a scientist to spread the message that we are killing birds, and if we kill the birds, they don't sing in spring, there are no hatchlings, and we have a silent spring. Well, the author of this breathtaking book is Rachel Carson, and I think she published it in 1960. So here is a bio of Rachel Carson. She was a biologist, ecologist, and excellent writer, and really way ahead of her time. In fact, Rachel Carson started the whole environmental science movement. One person who made a difference. And I have a couple of quotes, and I don't think I will repeat the quote. I'll just leave this image here for a few moments so you can read it. Here's a second quote. The point is, we are not spraying robins directly, but they accumulate DDT indirectly by eating earthworms, which have DDT in their fatty tissues. And here is a third quote. Well, recently we had the 50th anniversary of Rachel Carson's classic book, Silent Spring. And this scientist is honored by being on a postage stamp, which I show here in the bottom image. And I obtained this image from the website with the URL given here at the bottom. The font size of this text is too small, so it probably is difficult for you to read it, but this is a very good summary of the impact of Silent Spring. So I will stop for some seconds and give you an opportunity to read it. Rachel Carson makes the point that citizens should become better informed in aspects of sciences so they can make informed judgments that impact political decisions. And this is really a good argument for why I believe that enrichment chemistry is an important approach to teaching chemistry. We apply enrichment chemistry concepts to molecules in our environment, and a knowledge of such concepts will make us better informed citizens. I would like to mention one book which I really like among the multitude of books, and it's called Chemistry: An Environmental Perspective. I consider this hardcover book to be a unique general general chemistry book, and I recommend it highly to you. It is available at Amazon.com. Finally, I thank you for listening to this YouTube presentation, which is my first in my enrichment chemistry series on YouTube. Good day.